Okay, yesterday one of the slides I kind of glossed over, but I talked about the idea of how you detect EMR. And the two main ways of detecting EMR are directly and indirectly. So if I were to send out a signal, let's say I was capable of emitting EMR. I guess I probably do somehow, right? But let's say I emit, think of EMR as sound, right? As I emit EMR as sound, it's not actually EMR. You guys can all hear it because directly it's transferring to you. Does that make sense? Right? And so that's one way that you could actually detect this. But another way was indirectly. And one of the experiments I pointed out yesterday was the idea of sending light or some sort of laser or whatever it is, some sort of EMR, and reflecting it off of something else really far away, and then having it come back to you. And hopefully if it takes a long time, you can measure the amount of time it takes, measure the amount of distance it takes, and then we can figure out the speed of light. You guys remember that like big octagonal disc thing the guy was spinning mirrors of? That was an experiment of that. Today I want to talk similar along those lines, the idea that, well, EMR has these abilities to bounce off of things. Tomorrow we're going to talk about how it has the ability to bend. Not tomorrow, I guess Monday. That's the word refract. Then we'll talk about diffraction, which is like the ability to go around things. And so all of these are different properties of light or EMR where they don't necessarily travel in straight lines. Today, they will travel in straight lines, but then after they stop traveling in a straight line, they'll then bounce and go another direction. All of you, I think I've taught grade 11 math now at this point. What sort of graph was this where it bounces in a V? Absolute value. Absolute value. I think I did this with all of you guys. The idea of like if you were to graph this, if this was like a billiard ball or a pool ball or something like that, or I think we did one with an air hockey peg. Yeah, air hockey table with a bank shot, right? The idea that if it bounces in, it's going to bounce back out again, right? Particles do this, and light behaves as a particle. So therefore, this will bounce in and out. Okay. So the two main types of reflection I need you guys to know about are regular, which is known as either specular, or irregular, which is diffuse. So just to start, I want to illustrate a picture here. Imagine that this is a beautiful, calm day. You guys can see how light is obviously making the picture very similar when you see it bouncing off the water. Right? So this would be a good example of regular, a nice flat surface where everything bounces up perfectly. What happens if there's some ripples in the water? Well, I mean, can you still see some reflection? Sure, I can see that like this part of this tree over here is kind of sitting right in there. But is it like crystal clear? No. So I mean, here would be a good example of, yeah, it's reflecting, but it's not reflecting off of a nice flat surface. There's no calculations based on irregular diffusion that we're going to be talking about. Okay. So for the most part, we're going to assume that everything has a nice flat surface. But I mean, it is possible to reflect off of a curvy surface. It just means your picture is all distorted. I have a whole bunch of key terms I need you guys to know. And over the next ton of diagrams, because you might have noticed most of this is diagrams, I'll try to put these terminologies to use here. So first one, ray diagram. If we're going to try to show how light specifically bounces off a surface, that's a ray diagram. Incident is the light that is incoming. Reflected is the light that's outgoing. That makes sense. So light's going to come in, so that's incident. Then it's going to bounce off of, say, a lake, a mirror, something, I don't care what. And then it goes back out the other way. Does that make sense? So like if I were to draw a picture and it's going in like this is incident. Then it'll bounce the other way, and this will be reflected. Okay. Point of incidence would be right here. The point where incident becomes reflected. So that's like the point where it hits, I guess, the contact area. Normal lines, I actually have a couple of them drawn in this diagram right here. This right here, these little dotted lines here, are considered a normal line. So it's almost like what you want to do is find that point of incidence and draw a directly perpendicular line. There's a basic math principle then. If this angle right here is like, say, 10 degrees, then this angle right here is also 10 degrees. Does that make sense? Whatever angle it bounces in at, it'll be the same angle that it bounces out at. Even on some of these funky ones where it's kind of screwed up here, if this was 10 degrees, that would be 10 degrees. That's kind of this note right here. Your angle of incidence is always the same as your angle of reflection. And we're going to talk about this term a lot over the next little bit here. Are you seeing... How do I put this here? When you look in the mirror, you are seeing what we call a virtual image. Right? You are seeing yourself when you look in the mirror, obviously, right? But you're seeing a virtual image of yourself. Does that make sense? I'll come back to that more later. Alright, so here's some diagrams to start with. Imagine that an incident ray comes in here and bounces off of, say, a mirror, bounces back out. Incident going in, reflected ray going out, normal line perpendicular through it. If this was 15 degrees, that's 15 degrees. So far, so good in terms of terminology. Okay, let me talk about that term virtual image then. Imagine that you're looking in a mirror and you're standing right here and you're trying to look at this object sitting right here, this moon. You look in the mirror, what's going to happen to your vision is your vision is going to see the mirror, it's going to bounce off of here. Actually, that's kind of backwards. Because really what happens is light comes from here, the light will bounce off of the mirror, and the light will then go into your eye. Because light doesn't actually leave your eye. Does that make sense? Right? Like light is actually going into your eye. So some light will come off of this object, bounce off the mirror, go into your eye. Now, when you perceive this object, even though it is technically next to you, you are going to perceive it as though it's over here. Because when you see it in a mirror, it's going to seem like it's inside the mirror. Does that make sense at all? So we call that a virtual image, because what you're really seeing is an object like inside the mirror. So we have a convention for that. We use dotted lines whenever we're talking like inside a mirror, because there's no actual rays of light behind the mirror. Okay? There is not an object right here that light is coming off of and bouncing towards your eyes. Okay? Let's say that it was just your eyeball right here and there was no mirror and your friend was standing right here. You can see your friend because light will bounce off of your friend and go directly into your eye. Bouncing. Does that make sense? So therefore, when I look at you guys, you're not virtual images. You're actual people. That makes sense? But when I look off of a mirror and I can see some reflection, well, now, like if I look, imagine that's a mirror, and I see, like, say, Carlin's reflection in it, I'm actually going to see Carlin right there. But she's not right there. She's actually right there. Does that concept make sense? So that's kind of where the term virtual image is coming in. I have a whole bunch of animated things that I kind of stole, so I hope this makes sense. Just watch it a few times. Okay, so what I'm going for on this one here is describing the idea of a virtual image. Let's say that there's an image right there, and I don't care where it is that you're looking at it from. That light is then going to bounce off of that mirror. So, for example, let's say I am standing right here. Yes, the actual thing is right here, but I'm going to perceive it as though it's behind the mirror. I'm going to see it in the mirror. That makes sense? It doesn't matter where you're standing. I could be standing down here, and I would still perceive the image to be right there. I could be standing right here and perceive the image to be right here. Does that make sense what I'm going for here? The main thing I need to talk about here is two different terms. There's the image and there's the object. The actual object itself is this thing right here. This thing is the actual object itself. But when I see it, I'm going to perceive it as though it's right here. As though it's like behind the mirror, as though it's inside the mirror. That's what my brain is going to perceive it as. Does that make sense? Here's another diagram that I have that can hopefully help explain it. Say there's an object right here, and we're looking at it in a mirror. Okay. So if this person right here looks in the mirror, light would bounce off the object, hit over here, and this person would see it. Okay. But this person is not going to know that it's right here. When they see it in the mirror, they're really perceiving it as though there's an image behind the mirror. Does that Make sense? It's almost like when you look in a mirror and see yourself, really you see just an exact doppelganger of you. But if you're like 2 feet away from the mirror, really, it's like your mirror image is like 2 feet inside the mirror on the other side. Is this making sense? Okay. The point I want to make on this one right here then is that this object right here, if you're trying to bounce its light off of this guy over here, this guy standing right here won't actually see the image back here, will he? Because, I mean, let's say someone right here is standing right here. So let's say this is Chris. I would then be able to see light reflect off of here right there, but I'm going to perceive an image being back here. But let's say Ray is sitting over here and he tries looking into the mirror. He won't see anything, will he? Because this thing doesn't have the ability to bounce there to there because the mirror doesn't extend that far. And so that's why we call this a virtual image, because this image is not real to everybody. This guy over here would not be able to see the same thing in the mirror that this guy right here would be able to see. Let's say that Raj was standing right here. Would Raj see the same image? Yes. And in the exact same spot, because light would bounce off of here, bounce towards Raj, and Raj would be perceiving this thing in the exact same spot that Chris would be. Make sense? But Ray over here would not see the exact same thing. Okay, common places where you use mirror tricks then. Right? I mean, I think of like those fun houses, right, where they use mirrors to hide things. Magicians in particular. Think of how they might use mirrors to try to give the illusion that something is there and it's not. Okay, flat mirrors are pretty straightforward. There's not really a lot to add to them. I mean, for the most part, light bounces in, light bounces out. Okay, I imagine that if you're going to get tested on something difficult, it's going to be based on a curved mirror. Okay. You guys have seen these before at some point, I think, right? The idea of a convex concave mirror. You guys have seen these? Like, I found a picture here, like they put it up in the top corners of, say, a convenience store, so that you can, like, when you're standing, say, right here, light can bounce from here to there over to you, because it doesn't bounce quite the same way when it's a curved mirror, right? Same thing, you've ever like looked at your image inside a spoon, right? Sometimes you appear right side up, then you flip the spoon the other way, and you're upside down. You guys ever noticed that before? I'm going to talk about the theory behind that in a bit. Here's the terms you need to know. Convex and concave. Here's how I remember it. Concave is as though you're going in to a cave. Okay? And then by default, convex would then be if you were trying to go onto the other side of it. So like what kind of mirror is this one right here? Concave or convex? Convex. Yeah, because what's happening is this is like the outside curve of the mirror causing that sort of mirror. We often use like these kind of mirrors on like big trucks. We'll often have those as the side mirrors, convex mirrors, so they can see to the side a little bit better. Okay, more terms. A lot of terms. You know what? I'm just going to go to the diagrams and I'll come back to these ones here. Okay. All concave or convex mirrors are going to have what's called a focal point. And the focal point is going to be half of the radius. Okay. Imagine that this mirror was actually like a full circle. Okay. Obviously it's not, but imagine that it was, and I just drew the worst circle in the world. Okay. The center of the circle is the center of like what you'd always call a circle, right? So the distance from the center to the mirror would be known as the radius. Okay. It's actually not the center that matters so much. It's what's called this focal point, this F, this focus. And the focus is actually half of a radius. Okay. What we've discovered is this focal point has a lot of unique properties to it. Okay. Let me actually skip ahead. I want to show you a purpose here. Okay. You guys know how you have like headlights on your car? The way the headlights on your car work is that it's not just a light bulb that just shines outwards. There's actually a mirror inside your headlights. You ever noticed this before? Okay. When you go home, find a car and look inside the headlights. There's actually a mirror sitting inside there, a nice concave mirror. And what happens here is that the bulb is at the focal point. And when the bulb shines, if it shines and it hits the mirror, there's a property about focal points that anytime it hits a mirror, if it comes from a focal point, it always bounces out in parallel lines. So if light were to go here, it's going to come out in a parallel line. If it were to go here, it would come out that way. If it were to go here, it would come out this way. And basically what you get then is a very, very strong beam of light, because all of these rays that, like, this is where your car is, right? And this is the direction that you want the light to go. It actually bounces off the mirror before actually heading out very focused the other direction. Have you ever seen this before? We need a field trip and go look at some cars.
Most movie headlights have another mirror like in front of the bulb.
Yep.
Reflects it back onto the big mirror.
Yep. Often there's like a second mirror right here, where it will then go from here, bounce to there, and then there. Yeah. That way that the light is like all of the light is actually heading the direction you want it to. Because if you imagine a light bulb otherwise, like here's a light bulb. Light would go this way, 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 right? Well, if you're trying to travel this way, all of this light over here is not very helpful because it's going the wrong way. Does that make sense? So that's why in these headlamps, they actually put a mirror here. This is my definition of a mirror. So that all of this light will then hit the mirror and then bounce the way we actually want it to go. Okay, let me go back here. Kind of jumping around too much. So the focal point is like that half the radius point. Okay. The principal axis is defined as like the perpendicular line to a mirror. The vertex is where the axis meets the surface. The object is the actual source of the rays, and then the image is what you perceive. Let me do some more diagrams. Here's some of this stuff. Let's say you have an object. You have an object right here. And so what is going to happen here is light is going to bounce off of this object in all sorts of directions. Light's going to bounce this way, and this way, and this way, and this way. But I want to focus mostly on the rays that are going to go towards the mirror. Okay. One of the rays that's going to go towards the mirror is going to hit the mirror directly perpendicular. Well, we've discovered that anything that goes directly perpendicular into the mirror will always bounce through the focal point. But then there's an opposite property. Any light that goes through this focal point will actually bounce off perpendicularly. And what ends up happening is an object that is actually right here, you are going to perceive it as though it's upside down. Okay. This is for a concave. Okay. You actually probably have seen this before. I want to go back here. That's actually what's happening in this spoon right here. When you look at yourself in a spoon, you're actually going to see yourself upside down. Because what happens is some of the light is going to bounce and then reflect downwards, and some of the downwards light is actually going to reflect back upwards. And so it's actually going to flip the image, and you're going to see yourself upside down. So see if you can envision this in this picture right here. Here's you. Okay. Light from your head is going to reflect down here and go over here. So this is where your head is going to be. And then kind of similarly, light could also reflect here and to down there. And so your head is actually going to be here, and you're going to appear upside down. So that's how concave mirrors can actually flip an image upside down. That makes sense. I'm going to try to find a whole bunch of mirrors and do a bunch of demos. I'm not ready to do it yet, but sometime after Easter, I'm going to try to see that we can actually grab some mirrors and try to visualize this as well. Here's some image characteristics. It's possible then, using a mirror, that it could be the same size. But it's also possible to make objects seem bigger or smaller, depending on location and stuff. You guys probably know this already, I think, intuitively. The idea that, like, one of these mirrors right here, where's the... one of these mirrors right here. Everything's going to look a little bit smaller than it actually is. Right? Like, the actual size of this counter is not 2 inches, obviously. Right? It's actually a lot bigger. But you're going to perceive it as though it's very small. Right? But I mean, you've probably seen pictures of funhouse mirrors where like a person then stands in front of them and they're really big. Right? So you can actually enlarge images using these. So, where was I? So you can actually magnify things using these mirrors. You can also flip them. They can either stay upright, but it's also possible to flip a picture upside down in a mirror. Position also matters, which is like how far from the mirror's surface you're going to perceive this thing. That would be this distance right here. The actual object itself is right here, but it's going to be perceived as though it's right here. And then the other term I want to talk about is the type of image. There's what's called real and virtual images. A real image is what is like perceived as being in front of the mirror. This would be considered to be real. Whereas if you were somehow perceiving something as though it was like inside the mirror, that would be known as a virtual image, where it's not actually back there, but you're just perceiving it as though it is inside / behind the mirror. Here are the 3 golden rules of concave convex mirrors. And then we'll do some examples on this in a bit to help solidify it, because gathering this takes a while to process. If you have any ray that goes through let's start with number 1. If you have a ray that goes parallel to this axis, like this right here, this red line is the principal axis. If you ever have a ray that goes parallel to the axis, they always bounce back through the focal point. So like if I were to draw another ray like this, I know where it's going to bounce. It's going to bounce through the focal point. Does that make sense? If I had a ray down here, oh, that's horrible. Let me try that again. Here, I'll actually use the line tool here to make it work. If you have a ray that would be going like this, it's going to bounce through the focal point. Okay. So if it started here and went this way, it will always bounce through the focal point. So that's one rule we've discovered about these mirrors. So that's number 1. Second rule, get rid of all this stuff, is that anything that goes through the focal point will actually reflect parallel. So if you were to have this ray, like say this, going through the focal point, so the ray was going like this, through the focal point, the way it's going to bounce is it'll bounce out this way. That's rule number 2. And then the third rule we've discovered is that any ray that goes through the center of the circle, because remember this mirror is really just a big circle. It's only part of the circle though, right? If you have a ray that goes through the center of the circle, so the ray goes like this. Oops. Let me get that line thing here. Like this, like this, like this, like this, like this. Well, if it goes through the center, then it will actually bounce directly back the way it came. That makes sense? Okay, let's try some examples here. Actually, I got some more of these ideas first here, just to help visualize it. Okay, just let it run here. Okay, so watch it a few times here, and then I'll try to explain what's happening here. Here's an object. I don't care where you are standing. Does not matter where you're standing. Light is always going to go through the same intersection point. So see here how the light goes through this object? It's going to bounce to the focal point. And that means a person sitting here, too fast obviously. I don't think I can pause it unfortunately. Okay. All of these people are all going to perceive this object as though it's right here. They're going to feel like it's in front of them, even though technically the object is over here. Like if this guy looks for the object, he's going to see it in the mirror as though it's right here in front of him. But is the object actually right here? Well, no, the object is not actually right here. The object itself is actually right here. But when this guy looks, he has to look like here. Here's an eyeball. If he looks that way, he'll actually see the object. But if he wants to see it in the mirror, he has to look this way to see it in the mirror, so that it actually bounces up to see them there. Hey. Sean.
So that's what those mirror house mirrors are tricky. It's like they put something somewhere.
That it's not. Right? So the actual object is right here, but you're going to see it as though it's right here. So if this guy right here looks in this direction, the light from this object will then, where's the line it's going to be? Here it is. The light from this thing right here will then bounce off of the mirror, go through here, and so this guy has to look, like you have to actually face and look at this, and then you'll actually see the object over here. Whereas, let's see, where's another eyeball? This guy right here would actually have to look over there to see the object. So that means that the image he is going to see is going to like be right here. It's going to appear to him when he looks off the mirror as though it was right here in front of him. But it's not, because it's actually right there. Let me try the next
How
one.
does that work? Like, when you're looking at the mirror, does it actually look like it's like close to you?
Yeah, like it's going to look like it's, because this is going to be where your line of sight is going to be, right? So, right, like if my line of sight is looking that way, I might actually be able to see you over there. Does that make sense? Using one of these mirrors, right? So then in my line of sight, even though you're right there, in the mirror is going to make it seem like you're like where Heather is. Does that make sense?
Yeah.
Whereas if I use just a regular mirror would bounce completely differently. Does that make sense? Let me try another visual here. So, here's a candle. Okay. In terms of some of these rules here, one of the light waves of the candle would bounce off of this mirror here. Because it's parallel, it will bounce through the focus. Other light waves will radiate out, like they'll radiate out this way and this way and this way. All of this light is going to go in different directions. So the light that goes this way would bounce off of the mirror through the focus to here. Whereas other light might bounce through the focus and come parallel. Here's what's going to happen then is you're going to see this image as though it's upside down. And so a person who is, like this is an eyeball and someone is viewing right here, they're actually going to see this image right here. If they just looked that way, yeah, they'd just see the candle, right? So if I want to see Jack in a convex mirror and I'm looking right there, I could see Jack in a mirror way over there. I could just turn my head. But if I don't turn my head and I look in the convex mirror, Jack is going to appear as though he's like where the sink is. Because that's what my line of sight is going to make it appear as.
Do they convex me?
Concave will work too, but yes, this one's concave.
I think both can show it upside down.
One can show it upside down. This one's capable of showing it upside down. Because you can see like how these light waves work here. This top one is going to come down to here, and then this one is going to come down to here, so you'll see it upside down, but it is possible for it to be upright as well.
How do you know if it'll be upside down?
We're going to draw it. Okay. Here's another one. You're actually going to see this one enlarged, and it's going to appear as though it's behind the mirror. It's actually going to become a lot bigger when you look at it. And it's just based on how these lines go. See how this one right here, if this object right here is going to radiate straight light, it's going to bounce off back to the focus. Or if it were to go up here and bounce perpendicular, it's actually going to make an image seem larger. I feel like I'm going to need to pull up these mirrors just so we can test them. I might need to take a break here. Okay, how about this? Go take a break. I'm going to see whether I have some mirrors, whether we can just play around and test this for a second. Maybe that'll help.
Why does it make it?
Okay. You'll continue from here. Okay, so we just did some demos with some mirrors that I hope helped. Kind of sucks that not everyone can see those. Let's do a convex mirror. So similar sort of idea here. Let's say that you have an object right here. So there's just a person standing here. I don't care where you are. Everybody is going to perceive that there is an image behind the mirror here based on how reflections work. This person right here is going to have light bounce like this and this. But what they're going to see is if they aim their eye towards the mirror like this, it's going to feel like there's someone back here. But is the person actually back here? Well, no, the person is actually over here, which is kind of like what those mirrors in convenience stores do, right? You put them in the back corner there, and so the light bounces off of the person down underneath, up and over there. And so then you can actually see kind of like around a corner almost. That's what's happening here, is if this was like a corner right here, and this guy could not directly see this guy, but he could have the light ray bounce around and towards him, and he'll see him if he looks this direction at the mirror. He'll see him in this location in the mirror. Okay, so let's talk about some ray diagrams here, in case you need to interpret or draw one of these. So let's say that there is an object right here, and we just often draw arrows to represent an object. So here's an object. What is it going to look like when you see it? Is it going to be upside down? Is it going to be backwards? Is it going to be smaller or bigger? Here are the main 4 things you got to consider. Where was that slide? Here they are. You got to consider magnification. So will you see it bigger or smaller? Will it be upside down or normal? So we call that erect or inverted. Position, like how big is it going to seem, like how far away will it feel like it is from you? And then the type is real or virtual, which is basically, is it behind the mirror or in front of the mirror? I mean, either way, the object is not in either of those locations, obviously, right? So let's try this diagram here. Say there's this guy right here. The first line I would draw is I would draw a very perpendicular line. And in drawing that perpendicular line, it would then bounce through the focal point. Then I would draw a line through the focal point, and it would then bounce perpendicular. And then lastly, I would draw a line through the center, and the line through the center would actually bounce right back at you. What's going to happen then is this object will now be here. Like this point right here will now be right here. Well, it won't actually be there, right? We would call this the object, and this is where the image will appear to be. So in this example here, the image is going to be smaller. It's going to be inverted. And it would appear to be this distance away. I'm going to focus on distance later because we actually have a formula to calculate the distance away that it would appear to be. But we'll focus on that later. And is this a real image or a virtual image? We'd consider this to be a real, just based on the fact that the image is going to appear to be in front of the mirror. Let's try this one here. So here again, you have a guy, I don't care what it is, an object. Let's say the object is right here. Okay. When you draw these lines now, first I draw the first ray going parallel, but now the focal point, because it's now a convex mirror, the focal point is actually over here on this side now. So what's going to happen is the ray is actually going to bounce back this way, but we're going to draw a dotted line because of the fact that this is now a virtual image. And so the dotted line would go towards the focal point like this. The second ray I would draw would be attempting to draw directly towards the focal point. So imagine that I'm trying to draw this directly towards the focal point, but I can't actually reach this focal point. So instead, light will bounce back this way. But I'm going to draw my virtual line, keeping going here like this. And then the same one as the red line, the center should actually bounce right back on itself. And where all of these points converge is where this object will turn into this image. So when you see this thing, you'll see it in the mirror as something that is a virtual image. It will also be smaller, but it will be considered erect because it's in the same direction it was going before. So you're going to see a smaller version of it, right side up, a certain distance into the mirror.
Can you be upside down and convex?
I don't think so. That's not one of the possibilities. You can be upside down in a concave, though. I got more diagrams here, but why don't we do an example ourselves? Okay, so our goal here is let's figure out where this object would appear to be in this mirror. So this is supposed to be what sort of mirror, if I kind of elaborate it? Convex. Okay. So convex mirrors, I'm probably going to see the image inside the mirror. It's probably going to be smaller, but let's draw it out. So I have a ruler on mine. If you guys can grab a ruler, it would probably help. Some sort of straight edge. Okay, so first thing I'm going to want to do is draw a line parallel to where I start. What happens to parallel rays? They bounce through what?
Focal point.
They bounce through the focal point. So this one I'll bounce through the focal point. It's actually going to bounce like back this way here, but since the focal point is like inside the mirror, I'm going to draw this like this dashed line. Does that work for so far? Second one. I'm now going to draw it as though it tries to go through the focal point. So it's going to try to go through the focal point. Okay. But what's going to happen is it actually won't reach the focal point. It will then bounce off of the mirror perpendicular. So I need my dotted one again. Where is it? Line. Dotted. So as soon as it hits the mirror, it will be perpendicular.
Are we supposed to draw that big thing?
You probably don't have to. You could probably draw just the line from here to here and then skip the rest of it. Because like, we're going to have lines here that don't actually mean anything. It's just about their locations here. So just off the top, from the top again. This first red line is as though light was trying to go perpendicular. It will actually scatter backwards, attempting to go through the focal point. So that means this light will actually come from here. Light that comes from here actually came perpendicularly. But again, I'm going to draw it as though it's through the lens. The last one's the hardest one to do. We need to do the center of the circle. The center was not labeled. But what's the definition of the center? Times 2. The center is double the focal point. So what we need to do here is like, I'm going to make a line from here to here. I can do this. I don't know how you guys want to do this. And then I'm going to pick up that line and I'm going to put it right there. So a ruler will work. So now I actually know where the center is. This is the center over here now. When it comes to your diploma, since we don't do written response, you obviously won't have to draw this, but you might have to interpret one. So now for drawing this line, if this were to attempt to go to the center, it would actually bounce directly back on itself. Where is the image now? Yes. So here is where my object was. Here is where I will perceive the image to be. Is that something you guys can replicate? So let's talk characteristics then. Is it going to be bigger or smaller? This will be a smaller image, so this will be diminished.
How do you know it's smaller?
Because it used to be this tall, and now it's only this tall. So if you were to look into one of these mirrors, it's, you guys ever see like on mirrors that says objects in the mirror may appear smaller than they are, kind of thing? Right? That's kind of what's happening here, is that this, you're going to see an image in the mirror, and it's going to appear as though the thing is only this tall. But it's not actually that tall. It's actually taller than that in real life. It's just based on the way that these light rays are bouncing from the image into your eyes, it's going to appear to you to be smaller. So it's going to appear smaller. It's going to be upright. So we use the word erect for that. The distance, we're actually going to calculate this distance right here in a formula in a few minutes. We'll get to that. And lastly, is this a real or a virtual image? Yeah, by definition, we're going to call it a virtual image. Because it's behind the mirror, basically. Does that make sense? You can probably make up your own diagram to practice drawing this, but there's 3 main possibilities. The possibilities are you have a concave mirror and the object is really far away. And I think I have that one drawn out here. I'll just maybe go back and find it here. Here it is. So a far away image in a concave mirror will appear upside down. A very close object in a concave mirror will appear very large, but as a virtual image. And then the other possibility is if it's a convex mirror, it will appear inside the mirror and it'll actually become smaller. Because it used to be this tall, and now it's only this tall.
For the concave mirrors, is there still rays going through the center line?
Sure.
Or the center?
You said concave one?
Well, yeah, the other
So that would be
ones,
this one here?
They have the point there, but they don't
Okay,
have the,
so then if it did this,
does it not affect it?
then it would just basically bounce right back through it. So see how this now is actually going to
Okay.
still converge in the same spot then? I'll go to the very last slide. I actually have a picture to kind of summarize this. Here's the three main possibilities. I found this one online that hopefully will help. If you have a concave mirror and it's really far away, you can make an object appear upside down and smaller. If you put that same object really close to the mirror, it will appear upright but bigger. And then here is a convex mirror, and it's going to appear probably smaller and also inside the mirror as well. Those are kind of the three main possibilities. Does that work? Okay, let's talk the math equations because we got 10 minutes left. The equations are not hard, by the way. So we do have an equation then to figure out distances and heights and magnifications, and these are both on your data sheet here. You just have to know what you're talking about. Okay. DO is the distance from the actual object to the mirror, and DI is going to be the distance from the perceived image in the mirror to the mirror itself.
So is that distance where you see the little blue line?
Yeah, I drew that before here. This distance right here would be the distance of the image, whereas this distance right here would be the distance of the object. So you're going to perceive this thing, if this was like, say, 10 centimeters, you're going to perceive it as though it's maybe like 6 centimeters into the mirror. Makes sense? Kind of like when I was doing that flat mirror right there, right? Like I could put an object here, and then I said, I feel like I can reach it back there. We could actually calculate those distances. The other formula is about either magnification or heights or distances. So let me just walk you through some examples. Go for it.
So it's like the focal length, like you're on the two.
No, the focal length is actually the distance from here to here. That'll have to be given to you. Because that's like the curvature of the mirror. Some mirrors are very curved, whereas like others are a little bit more flat perhaps. You're almost guaranteed to be given this distance here. Oh, other notes here. If something is in front of the mirror, make it positive. If something is behind the mirror, make it negative.
So if like the focal distance is like 6 centimeters, negative 6 centimeters?
If it is a convex mirror, it would be negative 6 centimeters. Yeah. So let's try one here. We have a convex mirror, and it has a radius of 20 centimeters. So I'm just going to draw this out real quick. Here is a convex mirror, and like here is my object. I'll just make it be a person. So this is a convex mirror, and the radius is 20 centimeters. Where's the focal length going to be then? Half that. Good, yeah. So that means that my focal point right here is going to be half that, which is going to be 10 centimeters. But I'm going to call it negative 10 because it's like inside the mirror. Does that work? Okay, then the object is 30 centimeters in front of the mirror. So like I am 30 centimeters away, which is going to be like a plus 30. So now my question is, where will the image appear? So first I actually want to try to draw it out if I can. I'm just going to draw like my head as to where that would be. So this right here would go like that. And then like that. Does that make sense how I'm drawing it? First parallel, and it'll draw it into the focal point. Then I'm going to draw it as though it was going, ooh, I need a ruler for this. Line. Then I'm going to draw it as though it was supposed to be going directly to the focal point, but as soon as it hits the mirror, it will actually go parallel. Line. So let me draw this one. This one would go like that, and like that. This one would go like that, but as soon as it hits the mirror, it would then become parallel. And then lastly, if it went directly to the center, it would bounce back on itself. So I know it's a mess, but where did these lines all converge? Converging there. One is going from like top of my head directly to the center. which would be like right here. This would be the center right here. So the top of my head would appear to be where all these lines converge. They should all meet in the same spot, right? So if I then maybe like erase all of this because it is getting a little crazy. Might have to finish this tomorrow. Just move some of these out of the way. Let me move all these out of the way. If this was my head right here, I'm going to appear to be in the mirror right there. That makes sense? So I'm going to appear to be smaller. So first let's figure out where the image is going to appear. So the formula we need then is 1 over f equals 1 over d plus 1 over d. 1 over f equals 1 over d plus 1 over d, and 1 is of the object and 1 is of the image. I just want to double check something real quick just so I don't teach you it wrong. I'll make sure that should be negative. Sorry, bear with me. It's too important to get wrong today. Don't want that open. Okay. Okay, so let's plug in some numbers now. We know our focal length is negative 10 centimeters.
The focal length is from the focal point
To the actual mirror.
Yeah.
Okay. We know the distance to the actual object itself is 30 centimeters. And then we want to find the distance to the actual image. So how in the world do I isolate for di? We're going to have to do like negative 1 over 10 minus 1 over 30 equals 1 over di. Does that make sense how I'm bringing this guy to the other side? So if you guys have a calculator, what is minus a 10th minus a 30th? I don't have a calculator nearby. What'd you get? Minus 2 over 15? Give me a decimal though. What is that? Oh.
Negative 0.133.
Okay. That's equal to 1 over di. How do you get di by itself then? Yeah, you reciprocate it. Yeah, so then do like the whole to the minus 1 thing. So go negative 0.133333 to the negative 1. And that'll find you what your di is. What'd you guys get? Negative 7.5 though, right?
Yeah.
Negative 7.5 centimeters. Does that make sense? It's tricky because you got to use reciprocal buttons, Brad.
Is it necessary to convert into meters?
If I'm keeping in centimeters, I think it works the whole way through.
So what is this di then?
Okay, so this should be what di is equal to. So now let's go back to our picture. That would be the distance inside the meter, we believe is 7.5 centimeters. Kind of makes sense. As I drew it, it was before the focal length, which was 10 meters into the mirror. So this guy should be 7.5 centimeters into the mirror. Okay, let me do what part B, and we'll skip the next example. It's the same thing, it's just another example. Let me try doing part B here. The second part here is about if we actually know how long or like how tall the object is. Let me just move all this out of the way. So I kind of figured out the x direction. Now I want to figure out the y direction. If the object was 5 centimeters tall, so like for example, if I was only 5 centimeters, now my question is, well, how tall is this guy going to be? That makes sense? Okay, so that's the other formula. So the other formula here is, actually I just asked for the magnification. So the magnification would either be to the two heights divided by each other or the two distances divided by each other. So to find your magnification, it's equal to negative d I over do. Too far. Too far. Di over do. So your magnification is negative di would have been negative 7.5.
Would it be positive because it's already negative?
Right, okay, so double the negative, make it positive. And then do would have been 30. So your magnification is going to make it smaller.
What? It's a quarter.
A quarter? 0.25. So it made it a quarter as tall.
Centimeters?
Well, the magnification wouldn't have units. So you'd just say it's like a quarter as tall. A follow-up question I could then ask would be, how tall would this thing appear? So then what's a quarter of 5? Sure, so then you could say that if this thing is a quarter as big, this thing would appear to be 1.25 centimeters. If you were to actually go and try to measure the, like if you were to, stand here, right, then someone else goes up to the mirror, puts the ruler next to it, it would appear to be that big. The object itself is not actually 1.25 centimeters, right? But that's what you see in the mirror. Does that make sense? It's a tough lesson. Tomorrow we have Flex Friday. Why don't we just real quick do the second example tomorrow? And then after that I'll give you guys time to go wherever you need to go. Does that work? Okay. In terms of stuff though, write this down. It would probably help if you did some practice. It's not really, really hard, but it's one of those things where it takes a while to wrap your mind around. Like, the more examples you do, probably the better it is. So here's some examples to work on. So come here tomorrow first thing. We'll do the last example. We'll see whether it can help solidify it a bit. And then after that, if you guys want to go work on English or something, then take off from there. Does that work?